welcome to the Space Vehicle Mock-up facility at the Johnson Space Center in Houston, Texas. Thanks for joining us on today's Hangout. I'm Brandy Jean with NASA Public Affairs, and we're about 30 minutes away now from the most complicated test of Orion's parachute system that we've ever done. It's been delayed a bit this morning thanks to some issues with the support aircraft, but we should be able to see the drop live at about noon Eastern Time here in just a few minutes. And in the meantime, we're going to be taking your questions from social media under the hashtag Orion test. So start sending those in now. I'm sitting here in front of a mock-up of NASA's new Orion spacecraft, which we're building to take humans farther into space than we've ever been before. And what you see in the background, we actually use for testing here at Johnson Space Center. But in Kennedy Space Center in Florida, they're building the Orion that's actually going to be launched into space in December. When it is launched, it's going to travel 3,600 miles into space, which is the farthest that any spacecraft built for humans has been in more than 40 years, and then return to Earth at 20,000 miles per hour, enduring temperatures of 4,000 degrees Fahrenheit as it travels through the Earth's atmosphere. That's going to help us be sure that all the critical systems we need to send astronauts into deep space and eventually Mars on future missions are up to the challenge. But sometime between hitting the Earth's atmosphere at 20,000 miles per hour and splashing down in the Pacific Ocean, we need to slow the vehicle down to about 20 miles per hour, which is where the parachute system comes in that we're going to see in action today. Standing by in Yuma, Arizona, on the U.S. Army Yuma Proving Ground, we have Stu McClung. He is standing by to tell us more about the test. Stu is the Landing and Recovery Systems Functional Manager. And then here with me at Johnson Space Center, we also have Molly White, an Orion aerothermodynamics engineer, who can tell us some more about other tests that Orion's been going through and also give us an idea of what engineers are going to be getting back from that test flight in December. So we're going to start here with Stu, but remember that we'll be taking questions with the Orion test hashtag in just a few minutes. But first, let's go to Stu and see how things are looking there in Yuma. Stu?
Hey, good morning, Brandy. How do you hear me? Just do a quick voice check before I get going.
We hear you good here.
All right. Oh, good. Hey, thanks for joining us. You can see we're getting ready for the test. Like you mentioned, we had a short delay. One of the chase aircraft that we used to photograph the parachute deployment events had an issue, and so we had to sortie up another aircraft, and that caused us that slight delay. But they're making their approach runs now, and so we're getting close to a good test. Like you mentioned, this is one of our most challenging tests. This is number 14 in our series of 17 development tests. This one, we're primarily test objective is to look at how the jettison of the forward bay cover works. We've done that once. We've done it a few times on the ground up at the Lockheed Denver facility. This one, we've set up the test conditions to let the vehicle fall faster, get a higher dynamic pressure, and give us a more challenging test objective. And so we'll observe how the cover comes off, and then we'll also look at one other planned failure. We'll skip what we call a reefing stage on one of the three main parachutes, and that'll help us to get better correlation of our predictions and our models for parachute performance. And, let me pause. I'll let you ask me questions instead of me just talking.
Well, before we go to Molly, why don't you tell us a little bit about where you're standing?
All right. Yeah, I'm out in the southwestern part of Arizona. It's I don't think it's quite broken 100 degrees yet this morning. It will eventually. We're at Yuma Proving Ground. We work with the Army and utilize Yuma Proving Ground as our test facility. As, you know, we need it helps to have a large footprint when you're doing a parachute test like this. And so Yuma is a large multi-purpose test range, and we've partnered up with them. And we're out here north of Yuma, south of Quartzsite, if anybody's out there looking on Google Map. And so we're out there, and the test range is about a mile or two wide and 5 or 10 miles long. So that gives us the large footprint outside of a populated area where we can safely run these tests. We've been working with Yuma for quite some time now. They are a great host for us, and we have a pretty good partnership with them.
And the weather and everything is looking okay, and the aircraft issue's been cleared up, and we're going to be going at 11?
That's right. Aircraft issues aircraft issues cleared up. We're right at the border of our ground winds. Otherwise, the weather's looking fine. It's clear and sunny. It's a beautiful day out here, just getting a little hot and dry. After landing, one of our test constraints is to have ground winds that are low enough to allow the teams to safely recover the parachutes. The parachutes are effective enough that they can will reinflate on the ground, and it makes it hazardous for the recovery crews. So we're just at our limit. We're able to work underneath that, and so that'll be good. Each of these main parachutes is 116 feet in diameter, and so they, if you get one of these inflated, it captures a lot of wind and puts a pretty good load on the cargo, and you need to not have them whipping around when you're trying to recover them, because we take these chutes, all of our test hardware, we recover it, take it back to the hangar, investigate it, look for the not so obvious anomalies that we might find, and from all those small things we find, depending on what it is, we can modify our chute design and improve it, and just make it that much safer for the astronauts that will use these things on future missions.
Okay, well, I know you've been out to quite a few of these tests, probably, in your job. Can you give us an idea of what we'll be seeing in just a few minutes?
Can you repeat that for me? We had a small aircraft go over, and I didn't hear you totally clear.
Sure.
I didn't hear the end of your question.
I know that you've seen a number of these tests. Can you kind of describe what we'll be seeing in a few minutes?
All right.
What we should expect?
Yeah, so the short version of the test sequence, and as you mentioned, we start showing, use the parachute to slow us down to about 20 miles an hour. This test will start at 35,000 feet, so same altitude that a commercial airliner is flying at. We'll extract the vehicle from the C-17, and we'll let it start to fall. We have what we call programmer chutes that allow it to fall at a predetermined speed. We'll cut them away, and then we basically, at that point, get on test conditions. We'll let the vehicle drop a little bit more to gain some more speed. The forward bay cover will be, 3 forward bay cover chutes will deploy for a second and a half, and then we'll fire the thrusters that jettison the forward bay cover. As soon as it's out of the way, the drogue parachutes start to deploy. We ride the vehicle, or the vehicle rides down on those drogue chutes through that sequence. The 2 drogues cut away, and then the 3 pilot chutes are mortar deployed from the vehicle, and they pull the 3 big, large main parachutes out. And so Rad's we got our camera out here, and he's going to do his best to track it down. If he manages to get a video shot of the payload coming out of the airplane, it'd be quite an amazing feat, since he's got a 35,000 foot altitude moving target to deal with. But as soon as we get under main chutes, he'll be able to videotape it, and you'll be able to watch the final phase of the deployment.
About how long does the test take?
From the time we come out of the airplane till we're on the ground and the chutes are deflated, 7, 8, 9 minutes, something like that. It varies from test to test because we modify our test objectives, and so sometimes we let the vehicle fall farther, sometimes we'll start it higher up. If we fail a parachute, we'll drop faster. In this case, we're under 3 parachutes, and so our normal descent rate is 25 feet per second.
Pretty fast. So last question for you for now. Why don't you tell us what your role is in all of this?
All right. I'm, as you said, I'm the functional area manager. So within the Orion program, my area of responsibility is for all of the hardware that we build on the vehicle that is required for landing and recovery. So the parachute systems, the mortars, the uprighting bags that we use to make sure the vehicle gets into the proper position after we land in the ocean. My role is it's a mix of technical as well as schedule and cost. I try to balance our desires to have the safest system we can have with the available funds we got and within the schedule we have to support our mission. So I'm always one of the engineers that trade those different aspects of our design back and forth, and work with the team and, to, like I said, make it as safe as we can within the limits that we work under.
All right. Well, thanks so much. So now we're going to come back to Johnson Space Center for a few minutes and hear from Molly White, who is here with me. Molly, why don't you tell us a little bit about what you do?
Thanks, Brandy. Well, Stu has been talking a lot about the parachute test, which tests Orion from tens of thousands of feet on down to the surface of the Earth. We also need to know how Orion behaves from entry interface, or 400,000 feet, on down to once it's on the chutes. And Orion's first flight test this upcoming fall is going to tell us how Orion behaves in the actual flight environment before it gets down onto those parachutes. I work here at the Johnson Space Center for Orion Aerosciences, and we predict the aerodynamic and aerothermodynamic environments around the Orion crew vehicle and the launch abort system for design. We use a combination of computer simulations and wind tunnel testing to create those environments for design, but we actually don't know how well we did until we get that flight test data back. And once we get that flight test data back, we compare it to what our computer predictions and our wind tunnel test data told us to see how well the two matched up.
So what exactly are you looking for in the wind tunnel test? What does that tell you that you need to know before we go fly?
Yeah, for wind tunnel testing, we take scaled down models of either the launch abort system or the Orion crew module, anywhere from a couple of inches on to a couple of feet, which is obviously not the real size of the vehicle. And so we take temperature measurements, pressure measurements, we look at loading, lift and drag, and then we also look at heat transfer to the surface. And we take those measurements and try and scale them. We use various parameters and assumptions to scale them to flight. We also use our computers to predict what we saw in the wind tunnels, and we extrapolate that as well to flight. We say, okay, we did really well at predicting the wind tunnel test data, so we'll probably do well at predicting the flight test data. We don't know that exactly until we get the flight test data.
And all that's necessary before the actual launch in December, huh?
Right, and one of the things that we're working on right now, upcoming for the flight in December, is we're getting all of our processing scripts and everything and tools together to prepare for that flight test data, because it's going to be a pretty short turnaround between when we get that flight test data and when we're going to need to apply it for our design for Orion's second flight test after that.
Okay. Well, tell us a little bit about your background. How did you come into this job?
Well, I did my undergrad in aerospace engineering at Iowa State University, and while I was in undergrad, I got a co-op or kind of intern opportunity here at the Johnson Space Center, and I worked with the branch that I currently work with here at Johnson Space Center, and I loved the work that they do. It was very exciting. They were working on designing a real spacecraft to go farther than we've ever gone before in space and carry astronauts there and do missions and eventually go on to Mars. And so I was really just enthralled and caught up in that, and they offered me a job when I graduated, and I was ecstatic to accept it and come work here at the Johnson Space Center.
What's been the funnest thing you've worked on so far?
Probably one of the most exciting or fun things, other than this upcoming flight test, which I can't even imagine what it's going to feel like once we get that data back, was a wind tunnel test that we did where we took a scaled down size of the Orion crew module, like what you see behind me, only it was about 12 inches in diameter, so a lot smaller, and we took measurements where we created the reaction control system, which fires plumes and gases outside of the vehicle to orient it during reentry. Well, we fired those in the wind tunnel test and took measurements, and that was a really complicated, really extensive test, and getting those measurements back, looking at that data, and trying to apply it for the real vehicle was exciting. It was probably about a 2-year long project.
That does sound cool, but I guess probably you're really looking forward to the launch in December.
Definitely. I get kind of giddy a little bit thinking about it, and it's going to be something like we've never seen before.
All right, well, I think we've got still about 15 minutes left before we get to see the drop test. But in the meantime, we're going to be taking some questions from social media. Don't forget, you can send them in here on Google Plus or to Twitter using the hashtag Orion test. So send in your questions, and we'll see how many we can get answered before the drop test actually starts. I think we'll start with one from Twitter. It's why does NASA's spacecraft not use the Dragon landing technique of using rocket boosters to slow down the spacecraft? So I'm guessing that's probably a good one for Stu. Stu, did you copy that?
Yeah, repeat it one more time for me real quick, make sure I got it all.
Why doesn't Orion use thrusters to slow down and land instead of parachutes?
Okay, yeah, thank you. Actually, we looked at that. So I've worked on Orion since 2006 and 2007, and early in the program, we looked at that. When we were early in the program, we thought about land landing, and we traded land landing versus water landing. And for the types of missions that we're doing for deep space missions where mass is at a premium and we try to make the vehicle as light as we can, it turned out that a land landing was going to be about 1,500 pounds heavier for the vehicle, and so we chose to go away from a land landing capability as a nominal capability to save that mass. When we were looking at it, thrusters were an option, just like Dragon uses, just like the Soyuz uses. We evaluated that. We evaluated airbags and some other concepts as well. But at the end of the day, the trade was more of a decision to save the up mass and apply it to science and cargo.
Why don't you explain why the mass is so important to us?
All right. I mean, it's really mission dependent. If when your mission is carrying hardware to low Earth orbit, cargo and/or astronauts, depending on the vehicles you're sitting on, you have some other flexibilities in your design and your trade space to choose how much structure you put in, how much reusability, and when you're looking at a deep space mission, as we are, mass is more of a premium. You want to maximize the amount of cargo, astronauts, science that you can take to whatever that destination is, right? You've still got to lift it off the surface of the Earth, and so it ends up being a function of what's your primary goal. Back and forth low Earth orbit, which is a challenging mission in itself, but a deep space mission puts a different priority on taking mass out of your vehicle so you can maximize what you can carry with you for your longer duration missions.
That makes sense. So we've got a question from Anthony A. Gentry, who asked if even though Orion is designed to land on the ocean, if it could land on land if it had to.
Yes. You'll see in about 15 minutes. We clearly can. And you certainly can. The landing loads are different, but landing on land versus landing on water from a structural perspective isn't massively different. We still have you design for hitting soil, or you have to design for hitting into a wave. And so in either case, we take that into our design trades and protect for that. We'll target to land off the California coast, and so in general, it would take a fair number of failures for us to go long on our entry and land. Have a land landing. So we'll land off the west coast, and if something were to come up and we had what we call a ballistic entry, we would end up coming up short and landing further out in the ocean. But the capability exists. I'll say my parachutes don't care whether we land on land or land on water.
But I'm guessing it's a little easier for us to target an ocean landing since it's such a big ocean and no people living in it.
That's true, and when back to that first question, one of the reasons that land landing is a mass penalty is, again, when you're coming back from a deep space location, if you have an issue, you still have to protect for the ability of landing on water. Right? And so you've got to carry both systems. And so that was another reason we shifted to water only.
Okay. Well, we've got another question from Andrew Riley, who is asking for some detail. Let's see if we can quiz you on this, Stu. He says he's guessing that entering the atmosphere slows Orion down a lot, but how much? What speed will the vehicle be going at when the parachutes begin to deploy?
Let's see. We start our shoot sequence at around, on a normal mission, between 25 and 30,000 feet, and in the range of 350 miles per hour is when the initial parachute sequence starts. And so as you mentioned, we enter at around, for EFT1, we'll enter at 20,000 miles an hour, and come through the atmosphere, and that friction of sliding down through the atmosphere will have slowed us down to that point. That's assuming, Molly's got to get all of her predictions right for me. But assuming Molly did her work, and she's pretty smart, so I'm assuming she's got her numbers right. We're in the range of 350 when we deploy.
Okay, and kind of a related question. We have Hank Campbell on Twitter asking on behalf of his 11-year-old son who's watching, how heavy will Orion be when the parachutes deploy?
We have a landed mass in the range of 20,000 pounds. It varies a little bit, but that's a good round number to keep in your head. So 20,000 pounds is generally what I always talk about.
Okay, great. Let's see, we've got still about 9 minutes, I think, before the test, so we'll keep going. Keep sending your questions in with the hashtag OrionTest. Our next one's from Ben Etherington. His question is the forward bay cover recoverable or reusable? And that might be a good question to jump off of and talk about what all we might be able to reuse on Orion.
So the forward bay cover is recoverable. When we land in the ocean, the expectation is that the tile that are installed on top of it will maintain enough buoyancy that it will be able to recover it. We will clearly recover it here after the test today. It's not intended to be reusable. The parachutes that take it off are sized to be just big enough to get it off and do that job. They're not sized to give it a soft landing. So the cover hits at around 50 miles an hour. And so we would expect it to get some damage when it lands. And then just globally, we will reuse a lot of our computers and other avionics. Again, early in the program, we considered reusing the structure. And again, since this is a human vehicle, if you're going to reuse your structure, you need to inspect it, make sure that after a landing that all of your welds and other structural components are still intact. And the effort to inspect it is a lot of work, and is almost as much work as just knocking out a new piece of structure and building up around it. And so at the moment, primarily it's our avionics, which are some of the high dollar value items that are being reused.
Okay, and there was a second part to Ben's question. He said if we weren't going to reuse it, why give it parachutes?
The parachutes, and there are 3 parachutes and 3 thrusters, and they work in partnership to make sure you get the cover off. And the job of the cover all through the mission is to protect the forward bay, which includes the rest of the parachutes, from thermal environment, MMOD, just all the other environments that we have to protect for. And so it's got to get off and get out of the way for the rest of the chutes to do their job. I liken it to the first domino has to fall in a train of dominoes. And so it's, from the data that I've seen, parachutes alone could probably take the cover off. Thrusters alone could probably take it off, but we put them together to make sure that it gets off and gets out of the way and stays away from the vehicle. And I just got a call over the radio that I think we're 2 minutes from the start of the test.
2 minutes from the start of the test. Okay, well, while we're waiting on that, another question that we had was what happens if one of the parachutes fails?
Well, we actually designed that in. And certain tests we will plan those, planned and we'll demonstrate that. The vehicle assumes, the engineers that design the structure assume that one of our main parachutes will fail, and so they build the structure strong enough to survive a landing under 2 parachutes. All of our parachutes have redundancy built into them. We call it fault tolerance, and so if only one forward bay cover, if a forward bay cover chute doesn't work, we'll still deploy. If one of the 2 drogues fails to deploy, we'll still get on mains properly. And so that's part of our design activity. We are very close to starting the test.
Okay, we'll keep watching. Just for the viewers who are watching along with us, it'll probably be a bit of a challenge for us to lock onto it, but it looks like we see the craft there, and that's what Orion, or the test version of Orion, is inside of right now, and will be pushed out the back of for the test.
And I'll just give you a call as I can watch it if you'd like me to, Brandy. We're out of the airplane. A good initial extraction. In the test vehicle, the PTV is away from its sled. Coming down under the programmers. Looks good so far. We're still falling under the programmers. Just cut the programmers away. We're going to let it free fall for 10 seconds and accelerate.
And Stu, tell us again what that free fall does.
Free fall allows gravity to do its job and allow us to accelerate to our test condition. And the faster we let the vehicle fall, the more it is able to accelerate and give us a more representative test condition. So the more closely matches the flight entry that we'll see during EFT1. And we're under drogues. So we've had a good forward bay cover separation. I'm just tracking the PTV, the test vehicle, at the moment on my binoculars. And we just cut away.
3 pilots deployed, 3 main deployed.
3 pilots out. The mains have started inflating. Just heard the pop from the chute inflating. I don't know if Brad has this on camera. One chute's inflated, the other 2 are not yet. This was one of our other planned test objectives, which was simulating. Okay, good. Yeah, and so that's simulating what happens if one of the reefing stages opens prematurely for some reason, and if it skips a stage. Because we designed this assuming that the parachutes share the reefing. Yeah, thank you. Yeah, reefing is a way to open the parachute in gently or softly. If you went full open, think of going extremely fast and hitting your brakes really, really hard. You put a lot of energy into things, right? It's dumps a lot of energy both into the structure of the vehicle and in the parachute. And so we have ropes that constrain the diameter of the parachute, and they have pyrotechnic timers that allow them to open up, say, 10% initially, and then I think, I don't know if Molly remembers the exact number, I think it's 10 and then 20%, and then we go full open. And that allows you to open up the chutes gracefully and kind of more slowly spread the energy into the parachutes and into the vehicle. Again, by reefing, you kind of control and manage that energy, and it allows you to not design and carry quite as much mass in the system.
Well, it looks great from here. We're seeing a really good view. Thanks for getting that for us. I guess while we watch it make its way down to the ground, we can take a few more questions. We actually have one for Molly from Nick Lopez. It says, what kind of temperatures do you predict you'll see during entry based on your wind tunnel testing?
Well, we don't get up to the actual temperatures that we're going to see in flight in the wind tunnel test. But for EFT1, we're predicting a peak surface temperature of around 4,000 degrees Fahrenheit. That's 2 times the temperature of molten lava. And that's just for Orion's first flight test, which isn't going to completely stress the system as far as Orion will once we actually fly Orion's real missions out to the moon and beyond. For those missions, we're going to be seeing peak surface temperatures upwards of 5,000 to 5,200 degrees Fahrenheit.
So that brings up another question that we've gotten from Philip online, and he asked, how can the module be adapted for future missions? Does it need to change before the next flights?
Certain parts of the vehicle have already changed between the first flight test and what we're going to be flying on future missions. But the material that surrounds the vehicle, we call it its thermal protection system, and that's what protects it from those high temperatures on the surface. It's an insulative layer that's also designed to burn away and take that energy away from the surface. That thickness of that material can change depending on your mission, and then also we'll learn a lot from the Exploration Flight Test 1 or Orion's first flight test, and that will feed into the design for the future flight tests. We might need to adjust certain thicknesses or adjust what material is used for certain regions, and those are the design changes that we'll go into between the first flight test and the second flight test.
Great, and it looks like we've got the vehicle touched down now on the desert in Yuma. Everything looking good, Stu?
Yes, I don't know if you see so I'm assuming Brad's got the shot. You see 2 of the 3 parachutes, and they're just starting to deflate. And like I said, the ground winds here today are in the 7, 8, 9 knot range, and these parachutes are very effective. And so one of the things that we have to do is make sure we get them deflated, and the last 2 are hanging on for a little bit. But the vehicle's down. It was a good test. And I saw the forward bay cover. We obviously had a good clean separation. It's down on the ground already. Yeah.
So what would be happening now if this were the test flight in December and we were on the ocean? What would the recovery team be doing?
The recovery team, once the vehicle's down and once all the other objects are clear, so they know that there's no hazards, the recovery crews will take off out of the Navy ship that's in the landing area, and we'll be heading out in some small boats and Zodiacs to go and recover the forward bay cover, and then go and recover the vehicle itself. And so they'll come out to it in the boats and attach some flotation. Not the vehicle floats on its own, but some extra devices just to help stabilize it and prepare it to pull it back into the well deck of the ship. But they hold for a few minutes, just like our test team holds here. The mortar deployed parachutes have lids on top of them, and the 2 drogue mortars, for example, are about the size of a nice big trash can, and you've got to let the lids from those parachutes get out of the air and get down on the ground, so that you don't have to worry about a risk for the recovery crew to have one of these things come falling out of the sky. And so all these smaller parachutes and parts have to, we verify that they're down on the ground using radar and optics, and then we go out and start recovering the vehicle.
Well, we have, I think, maybe time for one more question, and we've got Simeon who's asked, are the parachutes usable in any type of weather or condition?
Yeah, actually they are. I mean, they would. We would not intentionally land in a bad weather situation, but the parachutes themselves will operate. They have temperature restrictions that you don't want to land. You don't want to put them out too hot. That's why we have the thermal protection system out there. But outside of that, on a cloudy day or a rainy day, they would be fine. They'll still inflate and do their function.
Okay, well, I think that's just about all we have time for, but before we go, I wanted, Stu, to get you to tell us about what's left to test now. I know we've got another test coming up in August. What will we be looking at then?
All right, in our August test, we'll plan to do two parachute main test. We're going to simulate one of our main parachute failures. We will look at some of our other design improvements we're putting in the system, and if we learn anything as we look at the hardware today and over the next couple of weeks that needs to be worked into the test in August, we'll blend that in. And then we have two more after that complete our development series. And once we're done with those, we'll take all of the lessons that we've learned and start building the final design that will go into the vehicle for EM1 and for our future human missions.
We can't wait to see all of that. I think we're going to wrap up there. So thanks so much for joining us for the Hangout and for sending in your questions. They were great. And especially thanks to Stu and Molly for taking time to talk with us. We're going to end with a look at some of the progress that Orion's been making this year and the preparations for December's launch, as well as some of what the Space Launch System and Ground Systems Development and Operation programs have been up to. So thanks again and have a great day.
All right, thanks.
Thanks, Brandy.